Hello and good morning, everybody, for a new edition. New section will probably be a shorter lecture today. So, what we have done so far last time was that we looked at classic approaches to object Viola and Jones face detector and parallel people gesture interact gradient. So all of those approaches follow the similar pipeline. First have to detect feature in your somebody said some sound problem. I will try to okay, let me persist sound or if it is better now. You get no sound at all, or is it just okay? Let me okay, let's try again. Test 1 2 3. Is it a bit better now? Maybe you have I put the noise threshold a bit lower, so maybe you have a bit more noise here, but hopefully it would be a bit better. If the volume on your side is too low, then maybe you can try your speaker settings here. Let's see. I'm usually in the yellow. I will put it a bit more anyway. Okay, thank you. So let's try with that then. Okay, actually now also the screen. So where we said that last week we looked at those three detectors, Viola Jones and Alan Turing's Hawk detector, and later the over feature detector, that all used an approach to first find features in the image and then some form of a classifier to classify those features into the objects that we wanted. For example, faces, non-faces, or people and non-people. And in order to work as an object detector, those approaches use the so-called sliding window technique. So that means you just go with a subregion over your image, and in each subregion you will try to detect the object. Is it there or is it not there? And then you have found the object in that region and you also classified it. Of course, this needs a lot of computation time, and so one goal of those approaches was to try to make it as fast as possible. And so Viola and Jones used some technique with some special feature detector, HAR features, with that integral image to have faster response of calculating the features, and then also this classifier chain or cascade that allows to rule out regions where there is no face relatively fast. And maybe a bit less clear in the histogram of gradient detector, there is also some benefit in the fact that the features are already calculated in a grid over the image, and then when you look at the specific region, you just look at the previously calculated features for that region, and then you don't have to calculate all the features again. But these sliding window approaches seem to be a bit maybe a bit brute force, that you really have to look at every sub window. So is there not something better? Overfeature went a little bit in that direction to also propose some bounding boxes, but it still uses some sliding window technique to find classified regions in some grid of the image. So today we will look at some new approaches which try to overcome this sliding window technique a bit. So, but maybe let's go again through that. So, what is actually our problem that we want to solve? We want to classify and localize object in the image. So, for example, if you have this region here, that's a dog, so you want to classify the dog, but you could also say it is a location task because you want to find the dog here and not at some other point in the image. So you have a classification and a localization that you would like to solve. And so if you use those sliding window approach as we have seen before, we could do that also with convolutional neural networks, which would be a bit maybe more the modern approach, but still then we would have to have some subregion, run it through the network, and then it should give the correct class. So here obviously should give cat. But there are a lot of different sub-windows, especially if you also consider different sizes to try. So even for a quite fast convolutional neural network, that could be a problem. So what can you do instead? So one idea that people then came up with was some region proposal. So you don't start from the image, just take an arbitrary region and try to classify it, but go up from the image and come with some meaningful proposals for bounding boxes where an object could be. So the idea is that you don't have to absolutely find the object, but you just have to find some reasonable proposals so that you do not miss an object. But many of the proposals could be false, and that then wouldn't be a problem. So if you, for example, just have 1,000 proposals, that's much better than the million of sub-windows you would have with a sliding window approach. And for those region proposals, there are different techniques here that have been evaluated. They all came around, so between 2012 and 2014. So, for example, some are based on search, some are also based just on segmentation. For example, this graph-based segmentation that we have looked upon when we started with the semantic segmentation and the segmentation. You remember with this graph-based approach, we get quite nice regions, and so those regions which then end up with the same color, or this, you could use those as proposals for a bounding box. So here, some idea, you will find some object here correctly. You will also have maybe some other bounding boxes here that do not correspond to object, but the segmentation algorithm has found. So the first approach then to use this for object detection and localization is called RCNN, so region CNN, CNN for the convolutional neural network. So what is the idea? You extract some region proposals from some other method. You compute then the features using the convolutional neural network. So they at that time did not use the network for classification, but just to calculate the features. Why? We will see. There could be maybe an improvement for that, but also for the features, you could calculate them as full resolution on the whole image and then go over to the regions. And then for classifying the region, they use the support vector machine using the features in that region that they have calculated with the convolutional neural networks. So the region proposal method that they used, there were any of some previously defined. So one of the best region proposal is really just the segmentation using this graph cut algorithms. So remember, if we had some exercise or at the end of the image you had a segmented image with graph cuts, and then you will just put you find regions there with a region which now all have the same color, and then that can give you the bounding box for that. And that you would use as proposal. There are some other methods here that use some other form of region proposals. But we will see this is just a start with the RCNN. Then later on, some other methods have been used for region proposals. So the idea is you have some region of interest proposals from some method, like 2,000 of them. Then first you warp those image regions. Why? Because your convolutional neural network is usually trained on some images of some specific size, and so it can only classify images of that size, so you have to warp them to that size here. Then you calculate the features by running those image regions through your convolutional neural network. And then when you have the features, you classify the regions using support vector machines. And then you train another thing for now to get the exact bounding boxes instead of the boxes from your region of interest proposal. You train regression to get the bounding box location. Okay, then you just get an update of okay, maybe our region proposal was not quite good. It should be more 10 pixels to the left and 5 up, and then this regression will solve for that. So these are some results of those RCNN approach, which are actually quite good, I would say. So I think we've seen the results before. So you could detect images of different sizes in different subregions here, and with usually quite a good accuracy rate. So the number here is the probability that the feature detector assigned then to that class. A bit more detailed, so the proposal regions are warped to images of that specific size, which was the size used then by the AlexNet, and they actually used the first few layers of the AlexNet to extract a feature vector, and then used those features for a support vector machine. So the network for the feature detection was pre-trained, so it was not trained on that actual data set for the object detection, but for some other image classification set. So this is usually called a transfer learning, and it is quite usual that you try to learn those feature detection stages of a neural network using some very large data set. And if you want then to specifically detect some different objects, then here they train a support vector machine. In other ways, you could train the last layers from the neural network to detect your object instead of the objects that it was originally trained on. And for the actual object detection, they used a support vector machine, which the different techniques for multi-classes, or different support vector machines with one class against all the others. And as mentioned before, the bounding box estimation was then treated as a regression problem. So that means there is a better localization for that. Okay, but I would say it also has some problems with that approach. So first, you train very different things. So you tune your network, you have trained it with some softmax, but then for your actual object detection, you use support vector machine, which has some other loss function. And then if you want to train the bounding box localization, which is a regression problem, you will have another loss function with a least square between the correct position and the position that you found. Also, it was a bit slow in training, and it was also a bit slow in inference. So inference will be at the time when you give it an image, and it should get the results. So it took about 47 seconds per image using the VGG 16 layers network. Okay, so what could you do next? I think quite a natural next step is that you kick out the support vector machine and instead use a fully connected neural network. And also to bring those problems together of the classification and the bounding box detection, you also put that in your network that you can use it for both. So start is still the same. You have your region of interest detector, then you have some convolutional layers to get your feature detector, and then you have some fully connected layers to train the classifier as a softmax or the bounding box as a regression here. So let's look at that again. So you would have your input image. You can go with your whole image now through your convolutional neural network to get your feature task. So that will be a bit more efficient. Probably could have also have done that with the other approach. Then you still have your region proposals from those proposal message. And now you just train the later stages of the network with fully connected layer to do the actual classification of your image regions. And you again treat the bounding box as a regression problem, but also you can also solve regression problems with neural networks. So you use the same layers here to get the softmax classification and the bounding box regression, which has a different loss function. So maybe I'm not sure if you have seen that before, or if it's the first time, but it's a often employed approach now, that you have some base network here for neural network, and then you have some different heads with loss function, and you try to minimize the loss function. All of the loss functions. So you can just take the sum of the loss function here and the sum of the and the loss function here, and then train the network on both those loss functions simultaneously. Okay, so in comparison then to the older methods, they get a bit a better score here, but the score is actually not so much better because support vector machine works quite good, but it was more gaining then on the computation time for that. Okay, so in this involvement of algorithms, what comes next? Well, you still have some other methods in your pipeline, namely the region proposal function, which is done by some other method. So can you also incorporate that in your structure with using neural networks? And so this is the last of those approaches of this RCNN family called faster RCNN, which then replaces the proposal region function also with a fully convolutional network using a region proposal network. So you have your image, you have some common convolutional layers which will give you features, and then from the features you first do some region proposals and then do some classification on those proposals, and as we will see, also get some finer bounding box predictions then from the proposals. So altogether, it looks like that. So you have different parts of the networks that then come together here. You have your proposals, and in order to better be able to train your proposal, you already try some form of classification here, which does not need to be so good, but which it helps to push the network in the direction that it can generate better proposals. And here you also have some regression loss if your proposal is then actually correct and contain the object. But you still use your proposal and then some more features here to get a more fine-tuned classification and then actually the bounding box that you want to have at the end. So, but you train this all together with 4 loss functions. One is this proposal network that has some coarse proposal bounding boxes, and just have a classification. Is there an object or is there no objects? And then the second part here, where you have the final classification with all the object classes and the final refined bounding boxes of your objects. Okay. So if today you see some results for RCNN, they would probably be the faster RCNN architecture. So maybe if we review all those RCNN approaches, we went to some combination of methods for region proposals, support vector machine for classification, and neural networks for the feature detection, to a method that just uses neural networks for everything, so for the proposal and for the final classification and for the final bounding boxes here. There is one more approach which is a bit similar, but from a different team. RFCNN, so region-based fully convolutional network. So they only used fully convolutional layers, which has the benefit of working then on images of any size, or bounding boxes of any size, and they predict some objects in some region of interest and then put those together. So they also use kind of 2 stages. They have some region proposals by some fully convolutional region proposal networks, which gives those regions of interest, and then they have a classification of region of interest into objects and background by a fully convolutional network. They used a larger network here, the ResNet 101. So as the name says, this has 101 layers, so it's quite a large network. And as with the approaches before, they use a pre-trained network on some large image dataset for classification, and then use this as the basis for the network, and then start optimizing this one. And they use, in detail, it's a bit more complicated. They divide your region of interest in some grid, and then every grid gets a score, and you combine all the scores to see the proposal then for the region. Why? Because it's fully convolutional, so you have a probability for every point in the image, and you need some way to accumulate that. Okay, so these approaches here, they worked on the proposals and then on classification, and then later there came 2 methods, YOLO, you only look once, and SSD, single shot detector, that try to approach it a little bit from a different angle. So not first to have the proposals and then the classification, but do everything at once. So that's why with the name here, you only look once. So you should have one single neural network that will predict both the bounding boxes and then the probabilities of the different object classes. And this should be very fast, and it actually is very fast. We will see then in comparison to the methods before, it has a good classification, but the localization part is not quite as good as the other approaches. But it's much faster and can run in real time. So what is the idea here between the YOLO approach? So first, you divide the image into a S by S grid, and S is given. So you have to select some grid size. And each grid can predict a number of bounding boxes, which is also fixed. So the bounding boxes then will have some width and height, and centered at that grid cell. What is the idea behind that? You cannot have arbitrary many objects. So if you have a sufficiently small grid cell, then maybe there is 1 or 2 objects in that grid cell, but there cannot be 100 different objects in that grid cell, and so that's why you only use a specified number of bounding boxes to propose the objects that are centered on this grid. The bounding boxes themselves can also be larger than the grid cell. Then each grid cell predicts a class probability independent of the bounding boxes of what is the object that's mainly in that cell. And then you have some probabilities for the bounding boxes and probabilities for the classes in the bounding boxes, in the cells in the bounding boxes, and then you just multiply them to get the probabilities of object and bounding boxes at test time, and you select those objects which are above some certain threshold. Okay, so you start with an input image here. You make this grid, so you can see it's not that fine, so it depends a bit on your image size and so what you want to select here. So here we have a 7 by 7 grid, so we have 49 cells. So first, for each of those 49 cells, the network predicts the class probability of that cell. So here it will be mostly dog. It could also be, if there is some overlapping region here, that there is some probability for dog or some probability for bicycle, because they could both occur in the same cell here. Then additional to the class probability map, you make the prediction of the bounding boxes also with the same neural network. So each cell can give 2 bounding boxes, and it can give the probability of those bounding boxes. So here it's drawn the one with some fat border here are the bounding boxes that are more probable, and the other ones are the ones that are less probable. But every cell will give 2 bounding boxes, and at the end you will multiply the probability of that bounding box here with the probability of all the cells in the bounding boxes, and this will give you the final probability and then the probabilities for the objects in this bounding box here. Okay. So YOLO results are actually quite good. As I said, sometimes the localization is not so good, but it's also not that bad. So here they tried, this is from the paper, so here they tried some person detector on some images, and that actually works quite good here. And also here with multiple object, generally works quite good. Sometimes it's a bit difficult, but that would also be difficult for a person. So here this object in the air that looks like it has wings is classified as an airplane and not as a person in a jumpsuit here. Or maybe their tank here is not recognized at all. Okay, we will see some more details of some new version of the YOLO done after the next one. So a very similar approach was done with this SSD single shot detector. They also divide the image in a S by S grid, and they use some standard bounding boxes that are given for each grid cell. So it's like some predefined bounding box, and then they use that as a starting point and then predict the offset and the confidence for each bounding box and object there. And claimed by themselves as others, they're faster and a bit more accurate than YOLO, or this is the version of YOLO there. So you similarly have a grid here. Then you predict a number of standard bounding boxes as a start, and then use that region of the bounding box to propose a modified bounding box with some scaling and small offset here, so new center position and width and height, and at the same time the probability for each object to be in that bounding box, so for each object class here. So here some results from the paper. Sorry, a bit small, but maybe you can zoom in a bit here. And also this detector is quite fast and quite good here in most of the cases. So even some persons, in some different pose or so, or here get recognized quite well. So after then the SSD came out in last year, Yala. Okay, sorry, some question. Yes, exactly. So that would be Y, not Z, but you have the center of the bounding box and the width and height of the bounding box that you propose for the network. So that will be as a result of the network, you will get those together with the confidence score there. So YOLO then came up with a bit a newer version that uses some higher resolution. It also incorporates a batch normalization. I think we looked at that also last time, which generally helps to train the networks, and it has some new basenet, so-called, their basenets are called darknet, so they train them themselves and not use one of the BGG or the ResNet model. And there is one for with 19, smaller one with 19 layers, and the larger one with 58 layers. So here maybe we can look quickly of how those networks are structured. So here is the 19. So you have convolutional layers and you have max pool layers, and with some different filter sizes. So I think we'll also discuss this next week quickly again. Some trick here that they use that also come from the Inception network is that you have some network which outputs a lot of features like 512, and if you have a 3x3 that will again go to 512 channels, that will be a lot of parameters. So what you can do is you can go from your 512 channels to 256 channels by a 1x1 convolution. Then you have something of the same size but less channel, and then go up again to 512 channels. And this is much less parameters than if you directly go from 512 to 512. Okay, there was another question about slide 33. Let me go back here quickly. Yes, oh, okay. I see, my mistake. Yes, that should be X and Y, which are then the prediction of the cells with some confidence. So it's like a vector of 5 results then for the bounding boxes, and times p for each bounding box. So that would be like the output of that here. So one output would be the xy coordinates, which are the center of the bounding box, which have to be inside the cell, because every cell can only predict 2 bounding boxes, but just the center has to be somewhere inside the cell, and of course it doesn't have to be exactly in the center of the cell, otherwise you would not have such a good localization. And then the width and the height of that bounding boxes, and the confidence that you have of that bounding boxes. So if it's, are you more sure that this is really the bounding box of the of an image, or like here that it's not a bounding box of the image. I'm not sure. The question was, can the width and height be as big as the image? Here I'm not sure if they have some constraint on the size of the image. you would have some problem if it's outside. So maybe they clip it that your bounding box cannot, as it looks like, overlap to the edge of the region of the image. But preferably it could be the whole image. But I think even if you only have one object in an image, you will probably be able to have some bounding box which is slightly smaller than the image. But I don't know what happens when it's exactly when your object is very, very big. Yeah. Okay, and this other network, the deeper one, which has just 58 layers, but which has a similar approach, except that it uses the trick of residual connections between the layers. These are those shortcuts that make it easier to learn than the correct function. So they divide it in some block, for example, as we have seen from a larger channels, again by one, less channels, again 3 by 3, and then some residual connection, and then repeat this like 8 times in between here. So this will give you quite a large network here. Okay, we actually had, I think now it's 2 years ago, we had some bachelor thesis that tried this object detection, and the idea was to have some mobile application that can take an image of some fridge, and it should give you the object so that you have in your fridge. Okay, so just the object, run then the detection, and then show the bounding boxes here. Then again, afterwards, we made some changes of what additional things you could use if you know what is in your fridge. So for example, you could check what do you not have anymore and put it automatically in some shopping list, or you could connect it to some recipe database and then give you some ideas. So what can I cook with those things that I have currently in my fridge here. So first of all, there they had to get some training data. So they asked all the other students and colleagues about images of their fridge and labeled them. And at the end, it turns out we have much more samples like for beer or so than for other things like vegetables here. So here is some test image. Here, that would be the ground truth that is labeled with everything that we had objects for in the fridge. So there could be 1 or 2 things that we didn't anticipate that people have it on the fridge, and so there is might not be a label for it. And if you compare, we see that the RFCN, so the approaches with the proposals here, they got quite a good detection and quite a lot of objects, while the 2 faster message, the single shot detector and the YOLO, get objects correctly, but not as many as the other approaches here. So if you compare, first of all, on the training set, they all were very good. So we measure here the mean average precision over all the classes, and on the validation set it was less good, so only about half as much detections, but the RFCN had about almost 50% of the correct detections, while the SSD and the YOLO had lower rates here, where YOLO was still a bit better here than the SSD. If you look at the inference time, then if you only do it on a CPU, then like for the RFCN, it takes 11 seconds to calculate that on a CPU, while for the others it takes 2 or 5 seconds. But if you do it then on a GPU, it's much faster because of the convolutional layers here. So even the RFCN, which is the full convolution network, is not so bad with like about 200 milliseconds, so you could do about 5 frames per second detection rate. But YOLO here is still a little bit faster. We also use some other GPU which has more memory, but actually not as fast computation power, so this was a bit slower then. Okay, as I said, a bit shorter today. For this was the first part of the theory. We will go quickly to some problems with your homework. But as exercise this time, I didn't want some special make your own network, because now all these convolution networks, they really take some time to train, as you might have seen with the texture detection. And so if you have a GPU and it's already training on that, then you probably don't have any more GPU power available. So let's try it in some pre-trained networks. So there is the YOLO that can be tried quite off the shelf to install it, and also this TensorFlow object detection page here. So if you want to try out the YOLO, you can just clone the repository and then make to build the actual detector. Then what you need is some weights. There might even be some new weights now that have been pre-trained, and then you can just call then in your directory you should have a method detect. You can call that on some image here, and it has some configuration of what it was trained on, like how many bounding boxes, what is the grid size. Of course, this also has to be known at the time to test on the image, and it needs the weights there. And I use that image that we have seen at the beginning of the lecture, and YOLO predicted that was not on a GPU in about 19 seconds, so that's a bit slow. Should be faster on the GPU, but it worked quite good to identify the dog, the two dogs and the cat here. Then there is also a page in TensorFlow for object detection, which has installation instructions. So if you follow this instruction and then run a detection in the notebook, you get that results, and you see that's quite similar. Again, the dogs and the cats were quite well detected here. Okay, so maybe as the end for those part in object detection, there is an interesting paper that lists a survey of all the object detection methods. So it's quite inclusive and has a lot of additional explanation if you're interested. So this is this paper here, and this is one slide from that paper, which is available online. So for all this history timeline of detection approaches, we looked at some early ones like the face detector of Vaiolo and Jones, and the Hawk detectors here, and then to the more modern one with first one to use neural network was the overfeature, and then we have the fast and faster RCNN, and then later the SSD and the YOLO approaches here. Okay, this is all for the object detection. So maybe in summary, we can say at the end we have those convolutional approaches for object detection that work with convolutional networks. Then at the end do all the stages of the projects, and basically the two approaches are either you first have some proposals of regions with your neural network, and then some classification in those proposals, or you have the grid-based method, which has just a number of bounding boxes by each grid, and then give you some classification on the bounding boxes and the grids to combine a score with where is the object and how probable the object is. Questions so far? So otherwise, I would like to point out maybe some things for the homework. So I don't know how far you are, if there's any problems. So first, okay, a question: could the UNET be a good approach for the homework? Well, the answer is yes, and you should try some approach actually that makes it faster, that makes it smaller and larger again, and this would be a unit. So even if you have connection to previous layers or not, that will both be possible. But you should do for the homework some network that will make the picture, that will make the images smaller using either some strides or pooling, and then do some upscaling or some unpooling there. More information of the exam. Okay, I'm not sure what I already mentioned last week. Okay, yes, it will be open book. It will be from home, and we will presumably do it as a quiz on Moodle. I don't know, we haven't received any dates yet, and we also have to check how to do the quizzes, but that would be the last information. So if nothing changes, which I don't think it will be like that. I'm sure to give more information then. Okay, yes, for the homework. So I mean, I think it's really maybe for some of you first time that you have to train something larger and longer. So just see if it goes and if it goes in the right direction. Not that you if it doesn't work or if it works, but you don't have to train it too long if you don't have the resources for that. So for your, if you just use the first data set, which is like the black and white, where we just cut the images in the middle, you will get, you should get the accuracy which should be better than chance. So you could calculate from the number of classes what the chance is, and this should be the accuracy that you will have at the start, but you will not get too far. So I don't know how that you might get some 10 or 15% accuracy, not so much. In last week's page on Moodle, I also included a method that will give you much more images and in color, and there you could get better results if you use that. But then it's even more training, and you have a larger data set. And so here I will quickly go through what you can use with a larger training set, because the small data set, it will actually fit in memory and you can train it from memory. But if you have then the larger data set, it will probably not fit in your memory. So you should you need a bit more efficient pipeline. And one possibility of a pipeline is the data sets in TensorFlow. I will see if I get the link directly to TensorFlow, but basically it is some structure that allows you to have a number of steps that will be optimized by TensorFlow and thus by Keras by reading the files into the main memory, maybe from disk, using the CPU, while the GPU is training the other thing. So I have thus, so you can actually copy that. So I put that in the function create dataset, and the idea is you have some list of images and some list of label images. Here I will just read them all from that directory. Make sure, because with the reading you never know, make sure that this list is sorted. And then I have this list. This is still only the list of image names as an array. And now I generate a data set that first has those image names in the data set. And then all other operations will be on that image. On the image files. I will shuffle them so I don't have the image always in the same order, and then I map my dataset to a new dataset by some function that will actually parse the images there. We will just see the parse function At the moment, we'll use a second manipulation step on the data set, which will put the images in the same size. As Keras needs to know the size of the images, it's good that your resulting tensor actually knows its shape. And if you have a network that calculates some border size, then from the label dataset I cut out the border here. And at the end do the one-hot encoding for the label classes. And here we see some parse function, and this is then actually the parse function. What does the parse function do? It reads an image, it decodes the image from PNG format so that we have it in as a raw data here. We convert it to float as it would be integer. We normalize it here. I don't normalize it by each image, but I just normalize the range to make sure that it's between -1 and +1, and then I also read the label file and decode the label file. And then in Keras, I can just use my create dataset function to make the dataset and then just fit the model using the dataset. And if you have validation data, you fit another dataset with the validation dataset here. We'll quickly see if there's some more information on the TensorFlow page. So actually here, if you go to TensorFlow and data, so there is a page on TensorFlow how to build an efficient input pipeline using that data set that we have just seen, which is a bit in more details of what you can do here. And our specific example was using images to get light. And just what is important is you can use those data set also directly in Keras. The advantage is this is just for structure, but you cannot load everything in the memory. So you need some tasks that will load your images and then give them to the training. Okay. Yes, so maybe if you have some more questions here. So one question here was a problem that the validation loss gets bigger while the validation accuracy stays the same. Yes, so that could happen, will happen. So maybe what you should look at is also your training loss and your training accuracy to see if you have some generalization gap. So if you have overfitting, and then maybe do some regularization if that is the case. Otherwise, I also have seen this, that the validation loss actually gets worse, but still the accuracy stays the same. So that's actually okay. It just means you probably shouldn't train too much longer, because you already reached the point where you will only have more generalization error. But I think this is also why it's really important to look at the metrics for the accuracy, because those are actually the ones that you want, and just the loss function can sometimes be a little bit misleading. I also seen that in the training loss function, it can go up again while the accuracy still gets better. So that would be okay. So just concentrate on the accuracy and don't train too long. And the bit regularization if you see a large difference between the training and validation accuracy. There was one question if you have a look at the Jupyter notebook. So which Jupyter notebook was that? So also, if you train, I think it's good to start with Jupyter Notebook, but maybe if you have really a long time with training, it could also help just to use regular Python instead of the Jupyter Notebook and just have some train function there. Then you can just let it run. Any more questions? Okay, if I get more information about the exam, I will let you know, and certainly at the end of the course. I think usually for the time it should be the same time then the course takes place. So it will probably be on a Tuesday morning again, but I don't know yet which one. So question, how do you include the validation data set in the fit generator? So okay, no, if you do it by data set, then you shouldn't use the fit generator, because you can use, if you use fit generators, then you will have to do it using an actual generator which has a yield to get the image and the label. So here I used fit and not fit generation, and then I can just give validation data, which can either be a NumPy array with a tuple of images and labels, or you can give it a data set. Okay, I will have to check on my notebook 2, which is not running at the moment, but I will come back to that. But it should be possible just to add the data set also in the fit generator. Okay, so the question is, if you add the validation data, then it crashes. Okay, but otherwise, I suggest I can look into that. I will look at my version with the fit generator, and otherwise I can answer directly on Discord then. But then I would at the moment close the stream in YouTube, but we can continue to discuss on Discord about the work. Okay, bye bye, and have a nice day.